Okay. So I'm recording. I put a note about this last week, I think, when I sent out the note about the recording of the lectures. And I don't usually like, I don't like to record my lectures and then post them when I teach a face-to-face class, because in the past when I've done that, you know, people just don't come to class. Why would you come to class if you can listen to a recording, right? Okay, which would be human nature. That's what we would all want to do because we have something else we would rather do. So typically I don't do it, but in light of the influx of all of the cases that we're having, we have people dropping out in the campus left and right. So should you find that you have to be quarantined for COVID reasons, then you can always zoom in on the class like I'm doing right now. And then I'm recording them and posting them to that playlist. So as an advantage, I suppose, for y'all, you know, you can always go through. These are not edited. They're not my edited videos. I have a channel. These are posted on my Precal channel, but these are not fancy videos. They're the lecture videos. So take it like you want. Go through it at 4 times the speed if you want, and sound like a chipmunk when you do that. Always fun. All right, now I'm going to hand back the quiz. I recorded the grades for the quiz. I don't have any grades recorded yet for Desmos. I recorded the grades for the quiz in Brightspace. Last name A, right? Javier A. Look over your quizzes. If you have questions, on the quiz, I'll be happy to talk with you about it after class. Pay attention to signs. The sign, you know, positive versus negative. That's not y'all's class, is it? Not statistics. This would be a good, okay. A good practice for types of questions that I can ask you on your quiz, or excuse me, the test. The test over this chapter is going to be next week sometime, right? Is it Wednesday or Tuesday of next week? Y'all remember? It's Tuesday, right? Right after Labor Day? Okay, that's what I thought. Okay, what's your last name? Okay. It's okay. I gotta learn the last name. Did the problems that came off of the quiz look familiar? Good.
Yes.
I was pleasantly surprised with the grades. I thought y'all did fairly well. Looks to me like you're grasping the concept. Yeah, you see what you're doing? Jamie. Everybody got their quiz back, right? All right. Okay, so we're gonna pick up where we left off yesterday. Kind of practicing some more of these translations or graphing of the sine and cosine. We'll practice a little bit more of them in class, and then we'll move on and cover the remaining 4 functions towards the in the latter half of class. Okay, and the Desmos activity that I posted is a how many of y'all have gotten in and looked at it? Some of you have, some of you haven't. Okay, so you should be able to get in, and it's a good practice for these translations and understanding how that affects the graph and so forth. So remember when we were talking about these functions yesterday, we were kind of breaking them up into their different components, where we were identifying amplitude, period, or B, so that we could then identify the period. We were looking at both vertical and horizontal shifts. And so the last, what would this be? The last one I want to do together as kind of a reminder of what we were doing yesterday is let's do a combination of all of that. Now, I will point out to you that I have this kind of written up here because those were all of the components that we would be trying to identify in our graphing function, in the function that we want to graph. But notice that when I have these equations up here, what I'm looking at is I want to identify by itself the B, right? I want to identify B. So if it is contained, like it will be in this equation we're fixing to work out, if it's contained in the argument right there along with our phase shift, you first need to factor that B out. That was kind of what we were doing the other day. We want to factor the B out, right? Like I have it shown up here in these equations so that I can identify the phase shift, okay? Because otherwise you'll get that problem wrong. So in this example right here, we have y is equal to -1 plus 2 times the sine of 4x plus pi, and I want to graph this over 2 periods. Okay, so I'm going to do 2 complete pictures of it. Now, you can see that in here, I have again that that B is contained inside of the argument or inside of that set of parentheses along with a phase shift. So the first thing that I'm going to do is I'm going to rewrite this as y is equal to -1 plus 2 sine and factor the 4 out. That leaves me with x plus pi over 4 inside of that set of parentheses. And now I have it to where I can identify all of those individual components. So A, what is A in this case? A is 2. Okay, A is 2. What else? We know that B is equal to 4. So the period of this function, which is 2 pi over B, which would be 2 pi over 4 or pi over 2, right? What else do we know?
See, you're tracking pi over 4.
Okay, so my phase shift. All right, so I've got a phase shift, which is going to be a minus pi over 4. And then what else do I have?
Vertical shift down 1.
I have a vertical shift, which is going to go down by 1. Okay. Now we're going to come back here and let's talk about the period. If I'm looking for the first set of numbers, my x scale, right? The values for my x-axis are going to fall between 0 and pi over 2. Right? That's how we took it. We took our period between 0 and pi over 2, and now I'm going to divide that up into fifths. So halfway between would be pi over 4, and halfway between 0 and pi over 4 is pi over 8. And then on the opposite side would be 3 pi over 8. So all I've done is divide up the interval between 0 and pi over 2 into 5 equal units, haven't I? Okay, and now I'm going to subtract the phase. So I'm going to subtract pi over 4. So when you do that, you should end up with, when you've done the subtraction, the leftmost point shifts to negative pi over 4, and then I'm going to get negative pi over 8, 0, pi over 8, and pi over 4. Okay, so those are the values that I'm going to come down here and I'm going to put on my graph. From negative pi over 4 to positive pi over 4, and then those numbers in between. Those are the numbers I'm going to be looking for you to make sure that you have written on your graph. When you do this on your test for me, I'm going to be looking for these values. Now I know that the amplitude is 2, but I had a vertical shift, and that's what I want to first put on my, that's what I first want to sketch on here. So I am shifting down by 1. I'm going to come down here to kind of get out of the way. And I am going to draw a line that's representing my shifted x-axis. It makes it easier for us to graph, okay? So this is my new temporary x-axis, and it's off of this x-axis that I am going to have an amplitude that rises up to, I'm going to go up by 2, and I'm going to go down by 2 off of that temporary axis, because 2 was the amplitude of this thing. So I would have a value up here at positive 1 and a value down here at negative 3. Now we're graphing sine, and it is not flipped or anything. So when we are graphing sine, sine is going to start at the leftmost point on our x-axis. So on our temporary x-axis in this case. And its maximum point is going to come all the way up here at 1. We are going to cross at 0, negative 1 on the y-axis. The minimum point is going to come down here at negative 3, positive pi over 8, I should say. And then we come back to the x-axis at pi over 4. So I have this, I was sketching it, it would look something like that. And then I would continue on either in both directions, one direction. What would I be adding to pi over 4 in order to come up with the next number? What would I have to add to that? I would add pi over 8. So when I added pi over 8, I would get this next number right here, right? 1/4 or 1/8, 2/8. So that'd be 3 pi over 8 next to that, wouldn't it? And I would just keep on going, right? Until I got a whole nother picture for sine right there. So this next one would be 3 pi over 8. And we would keep going. And that's how we would continue to do it for another period. All right. So when we think about this, that's kind of a review of what we were doing last time. You need to identify your amplitude. You need to identify B. And in this case, I had to factor out B, didn't I? 4 was B, and I factored it out in order to identify the period. Okay, if you've done any of the problems on the Desmos activity, you'll know that that is important, right? You don't get the same graph if you don't do that, okay? Identifying the phase shift. identifying the vertical shift, right? All of those components I'll be asking you about on your test to be able to identify them for me as well, and then graphing them. All right, are there questions on that? Well, get your calculators out if you don't have them out already. And I want to do a regression. You'll know what a regression is?
No.
All right. So a regression is, what if I said a line of best fit? Did you know what that is?
No.
Some of you know. Does anybody know what a line of best fit is?
Yes.
Yeah, all right. All right, so a line of best fit is if you take a sample of data right here and we come up with a mathematical model that fits the data. So it's a line or we'll learn that there's a curve, you can come up with a curve, it's just an equation of best fit, all right? You use a lot of regression modeling. So remember how I told you that everybody, it seems like in my world, is an engineer? Well, my husband uses regression modeling a bunch he works at the power plant on Lake Whitney. And so he gets data in on various things that are happening within the, on the controls, or I don't know, the stuff, the equipment, right? At the plant, and he has that he's able to model what should be going on with the with it. And so if he's looking at a trend and he knows what this trend should look like when something happens, like if they have a tube leak or if something happens to the equipment and it's not behaving in the way that it should, right? The data that he has coming in is not behaving like it should, then he's able to see that, okay, based on this trend that I'm used to, something is wrong. And then they can go out into the plant and they can try to figure out, what the problem is. So, you use a lot of trends. He uses a lot of trends. He uses it in Excel. So what we're going to do is using regressions. It's called a sign regression. In this particular case, it's called a sign regression. And so anytime we're doing this line of best fit, what we're doing is we're taking the data and we're coming up with an equation that can model the data. All right, that's the goal behind what we're going to do here. Now, what I have are monthly temperatures for New Orleans, where it says the maximum average temperature is 83 with a minimum of 53. The table below shows those average temperatures. We want to come up with an equation that is going to model the average temperature for New Orleans. I always wonder if this is real data. It says it is, but have any of y'all ever been to New Orleans in the middle of the summer?
I just
You gone in July?
yeah, it was in July.
Is it hot?
Yeah, it was miserable.
Miserably hot, right? Very hot and humid, right? That's why this 83 right here, I'm always looking at that going, these are lows, maybe these are the low temperatures. That's odd, but anyway, so we want to go through here and we want to figure out a scatter diagram and then create the function. Now, we're going to let the values, the temperatures be our dependent value, and we're going to let the numbers, the month, represent independent, right? So we have X being independent, that's our input value, and then we have the temperature being our dependent, that would be our Y value. And because we're putting this in our calculator, we're going to let January be 1, February be 2, and so forth. So we have 12 months here. Those are the numbers we're going to use. Now I'm going to put this over here sort of, and I'm going to pull up our calculators. Now, if you have, Javi, are you using the Inspire?
Yes, ma'am.
Okay, I don't know how to do a regression on the Inspire. All right, who else has an Inspire? Who else is
I can
using?
look it up real quick.
Okay. I think it's Javi. No,
And I
Or
left my
you can do it.
HDMI adapter at home.
that's okay. All right. So what we have here is, so I'm using an 84, all right? And what we want to do is we want to go to, let's see, I want to go to stat, edit, and I have a list. Oh, you can't see that, can you? Now you can see it, right? Okay, so I went to stat, edit, and you'll see that I have a list of values right there in my list. You all have a list? You have numbers? Some of you might, some of you may not. All right, if you have numbers in your list, I am going to use the up arrow.
Is it exponential regression, right?
It's going to be sine.
Sinusoidal regression?
Sinusoidal, yes.
Got it.
Okay, so I'm going to arrow up to the header of this, and I'm going to hit clear, enter. Don't hit delete. Don't hit delete, because you'll delete the list and then you have to do something special to get that list back, okay? I don't know. It's kind of hard. So I'm going to come over here, I'm going to arrow up, and I'm going to hit clear, and I'm going to go down, and it cleared the list. I'm not deleting the entries, I cleared the list, okay? So from here, I'm going to put my screen back on the other side, and we are going to enter those values. We're going to enter those values from one for the temperature. So you're going to enter in your list one. So L1 is always going to be your independent variable unless you set it up differently. So that's where we're going to put 1 through 12. It's always our independent. L1 is independent. L2 is going to be our dependent. Okay, L2 is going to be our dependent. So in other words, it's going to be the 12 temperature. So I want everybody to enter those into your calculators right now.
So do we put like the month 1 through 12 for the first column?
Exactly. I'm going to just put those in there. Okay, did everybody get those entered in? Yeah? All right. I'm gonna make mine bigger now. Okay, so all of the values should be entered into your list. And the first thing that we are asked to do is to create a scatter plot. All right, there's a couple of different ways you can do this. Let's try one of these ways. We'll see if this one works. So I'm going to go to y equals. If you have an equation on there, you need to delete those out. So I went to y equals, and I'm gonna clear it if I had equations in there. Now I'm gonna arrow up to plot 1. Does everybody see where I arrowed up to the top to plot 1? Okay, and I'm gonna hit enter and then arrow back down if it's not already on. Mine was already on because it was highlighted. So when I arrow back down, you should see that plot 1 is highlighted. Do we see that? Okay. All right. Let me just check one thing before I get. Okay. All right. So now I turned my plot on, the statistical part of this, all right? I turned the scatter plot on, and I'm gonna wanna go graph these plots, right? I'm gonna create a scatter plot, but I need to adjust my window so that I can see the dots in my window, okay? Now, let me think. I think I could do zoom stat. Let's try zoom stat, which is, so I went to zoom, and then I'm gonna choose option 9. Yeah, there we go. You get something that looks something like this, right? I've got some pretty little curve going out there. It's kind of obvious that when I'm looking at this, looks like a curve, right? Now, if I'm doing this in a lesson on graphing trig, it would be pretty obvious that we're going to create a sign regression on this. But generally, when you're creating equations or when you take data, you're going to create a scatter plot of your data to see what the data looks like, to know what type of regression to perform on it, okay? Because there's all sorts, you can do linear, quadratic, cubic, polynomial, so you can do all sorts of regressions. So we want to see what the data looks like to know what type of regression to perform on it. Okay, so here is my scatter plot. Now I want to come up with an equation representing the best fit for this data, okay? So I'm going to go back to stat. I'm going to arrow over to calc. And starting on line number 4, option number 4 is where I've got all of these regressions that I can try. So I'm going to actually hit the up arrow because it took me to the bottom of the list. And I'm going to choose a sign regression. So you can see all the options that we have here, but I'm interested in the sign regression. And now it brings me to this screen. For the most part, it should bring all of us to this screen. Does anybody not have that screen? I don't know, I'll look at it in. Does everybody have a screen that looks something like this? Most of you do? Okay. Okay. All right. Now, what this is telling us is that we are going to take our independent variable comes from L1, dependent comes from L2. I don't need to put anything in there except what I want to do is come down to the store regression equation part. Okay. And I want the calculator to work its magic on this regression, but I want that magic to appear magically on the y equals also. All right, so I want it to work its magic, come up with the equation, but put the equation on my graphing portion of the calculator. Okay, so I'm going to store the regression equation at, I'm going to choose alpha, and let's see, alpha 4. Yeah, alpha trace. And I have these options here. I'm going to tell it to store it on y1. All right, I did alpha trace. And I'm going to choose option 1 because that's where I want it to go. And then I'm going to hit calculate. Okay. So this is the magic of the calculator, right? All sorts of regression packages out there that do this thing for you. Okay. And it's even telling me, okay, I'm going to let A be given this. I'm identifying B inside of this. I'm identifying C's and D's, and it tells you the breakdown of the equation. I think you're all familiar enough with these types of things where you can plug them in and write that down. So if I were going to just, write this equation down and round it to the nearest, let's say, 2 decimal places, then the equation that models my data would be y is equal to what? 15.57 sine 0.51 x minus 2.02 plus 68.44. Right? That's the equation representing this rounded to 2 decimal places. Okay. Now understand that when I am creating this model, it is the model for best fit. It doesn't mean that it's always going to fit your data, right? Because you have data which would be real world, and we have a model which is math world, and they don't always match, do they? The real world and a mathematical model do not always match, all right? So there could be a little bit of difference there. Now, I want to go back in, since I put it on my calculator, I kind of want to see how well does this fit. Ugh. You know what? Okay, why do you suppose it did this? At first, I'm going to go, oh, what did I do wrong? But I know, because we've seen it time and time again. Let's go back. Change our mode to radians. There, that made more sense. All right, so to graph it, I had to have it in radian mode. So when it did not do what I thought it was supposed to do, that was an indication that I'm in the wrong mode. So to graph it, I need to be in radian mode. Now that's a pretty good fit, right? Looks like it's matching up fairly well. And then if I went in and I adjusted the window, so if I instead change the max to be, I don't know, let's go 50, and I go back and I graph this, right? That's the graph, that's the model for the data that we would be looking at. So you would be able to take 1 year's worth of data for New Orleans temperatures, average monthly temperature, and you could project then what it would be, right? That's the idea of modeling, is to be able to project or be able to, like I was telling you before, maybe be able to see what's going on, okay? So this is a regression. This is a sign regression in this particular case, modeling data, and we want to become familiar with being able to apply that kind of stuff. It's just heavy on the calculator commands is the only part that's really kind of difficult about it. Questions on that? All right. So what I want to see you all do, let's spend, we'll spend about a little time working on this. Maybe about 15 or 20 minutes. Okay. Well, let's see. All right, first thing I want you to do is I want you to graph this equation on your paper, okay? Graph this on your paper doing the same things that we've done before. Gonna give you about 5 minutes to get it graphed. You need to identify amplitude, period, phase, and vertical shift. And then sketch the graph over 2 periods. I want you to do number 1. And then once you think you've got it finished, check and make sure that yours and your answer matches your neighbor's. Now. Okay, so you come back to this. This is your function, right? What I do is on this side, set up that angle. To the right. If I have a third of it, what's happening? Basically. Or 1/3, one. Right. Okay, so you got that right. Now, we're going to come back and we're going to add that. All incremented by 1/6. 1/6. This is really 2/6. 3/6. If you don't know that, you have to add the middle number to your fraction. Not even survive that. So those are the 5 numbers. Okay. What's your base shift?
Yeah.
Okay. Shift that out. Now, that's another one of these. So I'm going to shift it. So this was a plus. So this is my phase shift. So we identify phase shift. Phase. And it's going to be opposite of the sign. So phase is going to be minus 5. So we're going to subtract 5 from the shift. Yes, it's going to be opposite, but you know you forgot to factor out the 3. That's what we started the lesson talking about. So if you remember back to the lesson at the beginning, where I said we needed to break it out so that we can out here. So I'm going to factor a 3 from each of these terms, put it on the outside. Bracket. You divide it, right?
So you put pi over 3.
Right.
And then you do the letter.
Yes, it's still moving to the left. But now you can identify B, so you know what the period is, and you know what the base is. All right, how are we doing?
But in it 2 periods, is it?
You have to draw 2 periods. You have to sketch, but we're only going to concentrate on 1 period, get that done, and then we'll add the other period on it.
I think that's the question.
Did you identify them for me? working on it. So if I ask you to identify what is you have to label this one. What's B? What's the face? No, that's the period one. 2 pi over 3. The one complete picture of sine is going to be between 0 and 2 pi over 3 before I overshift it. So 2 pi over 3, which you'll have to identify as well. The period one. That's important. Today is going to come from inside of the parentheses, right? It's the same thing that I was doing at the top. Okay. Go back to what I've written down before. All right. You about done with that? All right. So you should have something that looks like this. All right. If you don't have that, I want you to write down all of these components because this is exactly what I would be looking for on a test. You will not get credit for it if you can't show me all of these pieces. So you need to make sure that you're identifying the amplitude, the period, the phase. I'm going to want to see these values on your X and Y axis. Okay, clearly labeled. Don't just draw me a vertical and a horizontal line. You won't get credit for it. Because remember, all of this can be done again in your calculator. So I don't want to know that you can pull a picture off your calculator. I want to know that you can get these actual points, okay? I want to know the y-axis is labeled, and I want you to connect it with a curve. So if you don't have all of this stuff written down, get it written down right now before I change the screen. So amplitude would be 2, right? And it's flipped. So we're going to maximum value of +2, minimum of -2. Yeah. Okay. You got that written down? Okay. Next thing we're going to do is this is where you're going to put these answers on your paper. So everybody turn to, you either have a scratch piece of paper, like a whole piece of paper, or you turn to another piece of paper in your notebook, and you're going to answer some questions for me on your own piece of paper, and then you're going to hold them up for me like you're Vanna White, all right? And I'm going to look around the room because I have my contact in and I can actually see things. So I'm going to be looking to see if you got the answers right. So this is to yourself, you're going to work on this, okay? All right. So there are 4 graphs here and 4 equations. And I need you to match the equation with the graph. All right? Match each function or equation from 9, 10, 11, 12 with their graphs of A, B, C, and D. It might be helpful for you to go into each one of those and identify amplitude, period, vertical shifts, horizontal shifts, phase shifts, anything like that, so that you can identify out of the choices which goes with which, all right? So you're gonna just put number 9 goes with what letter, 10 goes with what letter, and so forth, and when you get ready, you'll hold them up and I'll tell you whether you got them right or wrong, okay? When you have them written down, write them big on your paper and hold them up and let me see. The first two. Yep.
Just hold it up.
Yeah, hold it up so I can see it. Yep, that's right. Hold them up for me.
You're the same.
Okay, then you're good. Yeah. Yeah, this is the one that's right. Yep. All right, think you got, anybody else want to try their answers up here? C, B, A, D. C, B, A, D. All right. Looking at period, looking at the period, looking at the amplitude, looking at the phase shift, really identifying off of the screen up there, what are the boundaries that you can see, right? To identify that. Okay, everything goes into that. Okay, the next one. Now I'm gonna match column 1 with column 2. Same thing, it's matching. Make it big when you show me. Yeah. Yeah. I'm gonna try to give you one. Yes. Get them? Yes. Yours the same as it? Okay. Last year. Uh-huh. The last year. The last year, correct. Yes. So did you factor those, Armando? Factor each of those? Because they both have a, so factor that out. All right, so you should have gotten B, D, C, A. Yes. B, D, C, A. All right. Yeah, maybe I thought you had. Sorry. I needed a different strength level on my figure it. All right, factor out. That's how you got it. See it? I was just trying to confuse you there. All right, well, that should be it. Oh, you had it out of order.
Yeah.
Oh. All right, so we're kind of practicing on that, right? Trying to recognize those components like that. Trying to recognize from a graph, you know, what would the function be? You've got a couple of problems like that in your Desmos activity. Those are great questions for you on a test, right? Because again, I know that you can plug some picture like this into a calculator. So how many of those do I really want to test you on? Okay, I want to know that could you take a picture and come up with an equation based on it, right? Can you answer various questions about a function like this? Can you identify the pieces of it? All right, those are the kinds of questions that I might be asking. Okay, questions on this? It's good practice. Make sure you're working on that Desmos activity. Any questions on, and so far, all we have been graphing was sine and cosine, right? Okay, well, now we're going to deal with the remaining function values. So there are 6 trig functions. We've only graphed 2 of them. And now we're going to talk about the remaining 4. This is what cosecant looks like. This is the graph of cosecant. So remind me, what is the reciprocal for cosecant? Sine, right? Sine is the reciprocal for a cosecant. Notice that when I'm graphing sine, sine starts at the origin. It has a maximum point, it crosses, it has a minimum point, and then it crosses again. And so what are you noticing about the relationship between our sine graph and this cosecant function? It's the reciprocal, but how are we going to, what do you notice about those x-intercepts on our sine function?
There's no x-intercept.
They're,
On the sine function,
On sign.
there's that one special word that I can't
asymptotes.
remember. Yes.
So everywhere there is an x-intercept for sine, right? Look at the x-axis. Everywhere there is an x-intercept for sine, there becomes an asymptote, a vertical asymptote for cosecant. Okay? And then everywhere we have a max or a min for sine, we have basically the vertex, I'm going to call it, of a bunch of these parabolas, because that's kind of what they look like, right? A bunch of parabolas, U-shapes, up or down. All right, so everywhere I have a max or a min is going to be the vertex of that particular parabola contained within the asymptote. So we're going to take graphing sine functions, what we know about graphing sine functions, to be able to construct the graph of a cosecant function. All right. Now, the domain where, let's see, notice where there are not values for cosecant. So all of these green U's represent the function for cosecant. Where are there not any values for cosecant? On the y-axis, where would there not be any values? Between -1 and +1. So there's like this void right here, right? There's this void right here where the maximum value I'm going to get from this direction is a -1, and the smallest value I'm going to get from this direction is a +1. So in other words, the domain of the function is going to be everywhere in between those asymptotes, right? If you're looking at the x-axis, it's everywhere in between those asymptotes. But the range or the output for the function is going to be between negative infinity to -1, and then from 1 to infinity. So if you remember when we read this, again, parentheses indicate I cannot include that value, so I don't ever include negative infinity, but I go all the way up to and including -1. Union, combining 1 to infinity. So those are the two output range values for my range, right? From there. And then because cosecant follows along with sine, it has a period of 2 pi. Technically, it doesn't have an amplitude, right? Amplitude is really defining for us that maximum value above my midpoint and the minimum value below my midpoint from sine and cosine. Well, we don't have that because we don't have a maximum value. You can see from the picture up here that the cosecant function is going to go off to y, go off to infinity, isn't it? To positive and negative infinity. So we never reach a max or a min. Okay. All right, so let's take that information and let's graph 1/2 cosecant x plus 4 . All right, we know that cosecant is the reciprocal of sine. It's kind of a nice idea to maybe think about that, all right? And we also know, even though I don't really need amplitude, I am going to identify what A is in this case. A is equal to 1/2. What is B? Okay, so if B is equal to 1, then the period is equal to 2 pi.
So where are you getting 2 pi from on the period?
Remember that we've defined period as 2 pi over B. Okay, so I'm looking at the interval then between 0 and 2 pi that I want to talk about. but I have a phase shift in here that's going to shift it to the left by pi over 4. So let's come in and let's identify the interval. Let's break up this interval. So I'm at 0, pi over 2, pi, 3 pi over 2, and from it, I am going to now subtract pi over 4. So you should get values from negative pi over 4, positive pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So those are the values that I'm going to come down here and I'm going to graph. Yes, sir?
What, if you're subtracting by pi over 4, if you're doing pi over 2 minus pi over 4, wouldn't it be pi over 6?
No, if I have 1/2 minus 1/4, I would have 1/4. Right? Okay. All right. So when I graph this, got negative pi over 4 to 7 pi over 4. I've got a 1/2 and a negative 1/2 that I need to make sure I put on my y-axis. And then I'm going to only use the dots for sine. So let's just put the dots in. We're not going to connect them. So sine is going to start over here at negative 4 pi. We have a maximum value at pi over 4, 1/2. Across the x-axis again at 3 pi over 4. We have a minimum value for sine at negative 1/2, 5 pi over 4, negative 1/2. And then we cross again at 7 pi over 4. Now, remember that everywhere I cross the x-axis, I'm going to go in and I'm going to sketch vertical asymptotes. So I'm going to come in here and everywhere there is an x-intercept, I'm going to draw a vertical dotted line indicating an asymptote. And then in between the asymptotes, so in between negative pi over 4 and 3 pi over 4, I'm going to sketch this parabola facing up using that vertex. And between 3 and 7 pi over 4, I'm going to sketch a parabola facing down using that as a vertex. Okay. And then you would just continue in the same fashion that we've done before, right? What would my, I'm going to be incrementing by pi over 2, or the next number, if you're following the pattern, would be 9 pi over 4, 11 pi over 4, and so forth, going in that direction, wouldn't it? Okay. And then in the opposite direction, it'd be negative 3 pi over 4, negative 5 pi over 4.
All you basically do is graph the sine graph and then just like do the arrows on the points by the asymptotes.
Exactly. That's how come we spent so much time talking about sine and cosine yesterday. Because we're going to use sine and cosine today to graph these. All right. So that's the idea. You graph sine, you just don't connect the dots and you draw your asymptotes. Okay. So let's look at secant. Now remember, what's the reciprocal for secant? Cosine. So if cosine is the reciprocal of secant, remember cosine started at its maximum on the y-axis, crosses the x-axis, and then has a minimum, goes back and crosses the x-axis and ends at its max. So once again, if you look at this, everywhere there's an x-intercept for cosine, I have a vertical asymptote. And again, everywhere I have a max or a min, I have a vertex, let's say, for each of my parabolas.
So it's
opening
basically
up.
the same thing like the secant,
Exactly,
the cosecant.
it's exactly like that, only we have to use cosine now to be able to graph it. So the properties of secant will be the same. Again, we have domains that are coming in between each of those asymptotes. Asymptotes mean I can't include them, right? I approach, but I never get those values. The range is still going to be between negative infinity and -1 and 1 to infinity, because we've got that dead space in the middle. Period's going to follow right along with cosine. And there's no amplitude again, because we don't have a maximum height or a minimum value, because it's going to move to infinity in both those directions. Okay, so now of the four functions we've talked about, sine, cosine, sine, cosine, secant, and cosecant, all of those functions have a period of 2 pi, don't they? All 4 of them. Okay. So let's graph this one. Y is equal to 3 secant of 2x. So this is cosine that we're thinking. The amplitude of cosine would be 3. B is equal to what? 2. So the period has to be
2.
2 pi over 2, which would be just pi, right?
So like, I don't understand, it's like, I understand pi is there, but like pi is not there on the equation, so like how is it still 2 pi over 2? Because like there was some just earlier that when you had the period, it didn't have pi in it.
Because we had maybe 2 pi right here, and pi was disappearing, right?
Okay.
Okay, the denominator for period is always going to be b. So if you identify what b is and b has a pi in it, then it's going to cause that to disappear. So this is pi. So I'm looking at an interval between 0 and pi. There's no phase shift and no vertical shifts on this. So I've got numbers between 0 and pi. Halfway in between is pi over 2. To the left is pi over 4. To the right is 3 pi over 4. We know that cosine has an amplitude of 3. And when I graph cosine, we're going to start on the y-axis at its max point. We cross, we find its minimum point at pi over 2, -3. We cross the x-axis again, and we end at our max point at pi 3. So everywhere there is an x-axis intercept, everywhere there's an x-intercept, we draw our vertical asymptotes. And then these always look funny because in between, the only full graph that I have in between here is falling between pi and 3 pi over 4. So that's the only one that's bounded on both sides by an asymptote. Over here at 0, 3, I only have technically a half a one. And then over here at pi, I have another half, right? Because I don't have that either right side or left side asymptote to be able to draw it. So you just draw it as a half one like that. And then if you continue on and you do this over 2 periods, you can either tack it onto one side. Like I said, you could split it between the two. As long as you end up with those other asymptotes, you can complete the U, okay? So this is secant. Same thing as cosine. The other one's the same thing as sine. It's pretty repetitive, right? How you feel about that? You got those down? Yes? All right. So this is tangent.
Oh, yeah, that's fun.
Tangent. Okay. A couple of things I want to point out to you on tangent. The first thing is the period for tangent is only going to be pi. So the picture for tangent, one complete picture is just pi. All right. And if you'll notice here, the domain is going to fall again between these asymptotes, but the range is going to go to positive and negative infinity. There's no stopping here in either direction. I always look at these and think of them more like a cubic function, right? These are similar in shape to a cubic function, and it's similar to a positive cubic function, right? Cubic functions come from the left, quadrant 3, I would say, they cross and then they scoot off to the right, quadrant 1. Now, the one distinction I want you to recognize is for the tangent function, when we look at tangent, center your focus in on the origin here. Focus in at the XY axis. And you'll notice that tangent, we're going to call it the parent function of tangent, is crossing here at the x-axis, right? And it's bounded on the left and the right by asymptotes that are falling at negative pi over 2 and positive pi over 2. And so if I were to say, if I traveled from negative pi over 2 to pi over 2, that is a distance of pi, correct? All right, so for tangent, one complete tangent, one complete period for tangent is just this single curve bounded on the left and the right by your asymptotes. Okay, so that's one complete picture. Typically, when I ask you to graph these for me, I'll ask you to graph like 2 or 3 of them. All right, so you're just going through it and repeating that. Now it's important, and I would probably make sure that you have got at least the center one on your paper, but I would identify this left asymptote as negative pi over 2 and the right asymptote as pi over 2 on your paper, and you'll see why in just a second. All right, so if you don't have those extra ones that I put on there, I would put them on there right now. So we're going to completely change the steps for graphing tangent and cotangent. And these are the steps that we're going to follow. So sine, cosine, secant, and cosecant follow pretty much the same process. We are now going to do a new process. So the first thing that you have to do is you have to figure out what the period is. Just like in sine and cosine, the period was 2 pi over b. And when I messed with b, I was either stretching it or compressing one complete picture, right? That's exactly what we're going to be doing here. So this time the period for tangent is pi over b. Then once you've found the period, then you locate the asymptotes, and we locate the equation for the asymptotes, right? Vertical lines. We locate the equations for those vertical asymptotes by taking bx is equal to negative and positive 2, pi over 2. Once you've done that, then you sketch it. All the rest of those steps don't really matter. You'll end up seeing how we do it. I would say the most important part falls here, steps 1 and 2. Okay, so just make sure you've got those ideas written down. Make sure that you have for tangent, make sure that you have the equations for the asymptotes. Okay, now I'm gonna move on because those are the two things I wanted you to make sure you wrote down, the period and the equations. Now let's go ahead and let's graph these. So if I want to graph y is equal to tan 2x over 3 periods, first I'm gonna identify, just because I'm in the habit of it, I don't need it necessarily. A is equal to 1. I don't need to know that very much, but I just do it. B, what's B in this case?
2.
Okay, so B is 2, then the period, which is defined as pi over B, has to be pi over 2. So that's going to be step 1. Step 2 is about the asymptotes. So the asymptote, which is going to be bx or 2x it's 2x is equal to negative pi over 2, and 2x is equal to positive pi over 2. I'm going to solve for x, right? I'm going to find the equations for each of the vertical asymptotes here. So on the left equation, if I divide by 2, that's like multiplying by 1/2, or in other words, negative pi over 4. And then the same thing, positive pi over 4. So now I shrunk one complete picture, didn't I? Which makes sense because I decreased the size of my period. So I had to decrease where those asymptotes were falling. Okay.
Wait, I'm sorry, I don't understand. You're dividing 2 on the x side and then.
So I have two separate equations here, right? So I divided by 2 and I divided by 2. If I divide by 2, that's the same thing as multiplying by 1/2. And so 1/2 times 1/2 would be 1/4, right? It should be pi over 4, by the way, if that's what was confusing you, Jim. All right, so now we come down here and we have our x-axis. We know that we have vertical asymptotes, which are falling at negative pi over 4 and positive pi over 4. Halfway in between is 0, right? So that's the other thing that I want to have labeled on here. All right, so I'm going to come on here and I'm going to draw my vertical asymptote at at negative pi over 4 and positive pi over 4. This is a tangent function, and so I don't really care about really anything else except the shape and the direction. So this is going to be a positive function crossing at 0, and that's all I really need. Now, as I go, if I wanted to graph this again, then I would add 1 period, or I would add, what is our period? Pi over 2 to pi over 4, right? So a period in this case is pi over 2, yes? So the next asymptote, if I'm moving in that direction, is going to occur at 3 pi over 4. Because for tangent, remember, it's only bounded left and right by these two asymptotes.
Give it extra pencil, mine ran out of lead.
Yes, I have one here. If you want to come get it. And then halfway in between pi over 4, you have what? You're welcome. What else do I have in between? What's halfway in between 1/4 and 3/4?
Pi over 2.
Pi over 2. So this is crossing at pi over 2. Can you see what we're doing there? Okay. Let's look at another one. So that one is just adjusting the period, right? Now, if we look at this next example right here, this next example is going to be an example of not only adjusting the period, but a phase shift. So notice that B is contained in the argument with the phase shift. We want to factor that out, just like we were doing before. So we're going to rewrite this as y is equal to tan of 2 times x minus pi over 2. There's going to be a lot of 2's in this example and halves. So the first thing, I know A is equal to 1. Again, you don't have to do that, it's just a habit of mine. But I do want to identify B. B is equal to 2. Therefore, the period is equal to pi over 2. And I have a phase shift of positive pi over 2. So if the second step is the asymptotes, let's only deal with finding the asymptotes, the equation for the vertical asymptotes. We know that that's going to be 2x is equal to negative pi over 2 and positive pi over 2.
Are you doing that because it's the period or the, or I guess it's just the period? Is where you're getting that pi over 2?
No, I'm getting that from the beginning, where I said you need to write down the equations for the asymptotes. I mean, technically, it's the period from the left to the right, but, okay. This pi over 2 came from the original equation and not from our period. All right. So the asymptote is going to be x is equal to negative pi over 4
What is that? Angle?
ASY asymptote,
Okay.
and x is equal to positive pi over 4. We just did that one, right? In the previous example, we just did those same asymptotes. But now I've got a phase shift that I am going to add pi over 2 to each of these asymptotes. Remember, the phase shift is taking the entire graph and shifting it left or right. So if the asymptotes are the boundaries that I'm looking at left and right, let's move the boundaries. So we're doing, we're just moving these vertical boundaries. All right, so now I'm going to have asymptotes that fall at positive pi over 4 and positive 3 pi over 4.
Sorry.
It's okay. And that's what we're going to graph. So we had to find what the period was, adjust the left and right boundaries of the period, and then we just moved the boundaries left to the right by a value. So when I graph this, I can come to pi over 4, 3 pi over 4. Halfway in between, we already know is pi over 2. This is positive, tangent is positive. So I would increase it like that. I could make another boundary over here at negative pi over 4 and another one over here, asymptote at 5 pi over 4. And that's what I would be looking for. Okay? Start with 1. Get 1 drawn, just like we did with sine, just like we do with cosine, and then add to it. Okay? If you don't, sometimes you get kind of lost on what it is, where you're supposed to put asymptotes and all those things. Okay? Okay. let's look at this one. I want you to graph it, but let's work on getting the components set up, okay? So this is the graph of 1 minus tan x. So I know that A is 1, again, it doesn't matter, but I do also need to point out that this is going to be flipped. It's going to be reflected, right, across the x-axis. Okay. I know that B is equal to 1, so the period has to just be equal to pi. And then I also know that there is a vertical shift down by 1. So I'm reflecting it and shifting it down. Everybody see where the vertical shift came from? Remember, it's that number that I'm adding to the function. So this 1.
Shouldn't be up.
Oh, it should be up. Up by 1. Now you see it, don't you? So the second thing is about the asymptotes. So bx, or just x, is equal to negative pi over 2 and positive pi over 2. And that's all I've got so far, right? I didn't have a phase shift. This
So
one,
where do you get the two x values? Exactly, like, do you get them from like a pi over 2, like, do you get them from the period over 2, or?
so remember it was bx is equal to positive and negative pi over 2 from the beginning when I told you that. And so if we substitute in 1 for x, then we end up with negative pi over 2 for one asymptote and positive pi over 2 for the
Oh,
second.
so it's just negative or positive b over 2, you know, both values, like,
Yes,
okay.
remember it's on both sides, surrounds left and right, the tangent function, which is passing through 0, right?
Yes, ma'am.
That's going to be important in a second. Okay, so let's come down here. I've got my values of negative pi over 2 and positive pi over 2. Those are going to be my asymptotes. But we had a vertical shift, didn't we? So I'm going to come up here to the value of 1 on my y-axis. And this is where my new x-axis is going to be at, right? Because I shifted the x-axis up. So I can put in my asymptotes. And I know that I also need to label where this thing is going to cross. And because it's halfway in between negative and positive pi over 2, we're going to actually cross on our translated on our temporary x-axis, right? So how will I sketch this now? Okay, so is it going to go from quadrant 3 to quadrant 1? Picture that. Or is it going to come from quadrant 2 to quadrant 4? Right, because it's reflected. So it's going to look like that. And then we will repeat that. And you would have yours here. Your graphs. Right? So that's tangent. Looks like, and that was the reflected tangent. So, So now we have the reflected tangent, right? And look at cotangent. They look the same, don't they? Okay, so cotangent looks like a reflection of tangent, all right? Cotangent, but the ways that you can kind of identify this one are some of the key aspects for cotangent. You still have all the same properties as far as the domain, the range, the period is going to be the same as tangent was for cotangent, okay? But notice that instead of cotangent passing through the origin, okay, we now have cotangent shifted to the right, if you're looking at it in terms of this. And so the leftmost boundary, let's say, would be here at 0. So the asymptote that I have here would be at 0 and pi. So I took tangent and I moved it to the right by pi over 2, right? I shifted it to the right. So now we've got two new sets of equations for asymptotes. They're not the same, are they? In order for me to calculate the asymptotes for cotangent, I need to be able to visualize where this is occurring at. Their asymptotes, before I move it, are occurring at 0 and pi. And then halfway in between would be pi over 2. So when you think about the formulas you need to understand, the steps are going to be the same. To determine the period is going to be the same, except this time the asymptotes are found by taking bx is equal to 0 and pi. And that's because we shifted it, all right? Which is why I keep trying to point this out for you to remember this, okay? So you don't get a formula card on this test. You got to remember this, right? You got to memorize this part. So just like before, we're going to follow the same process. We'll follow the same process of graphing cotangent that we did tangent. Okay, you got that written down? All right, so we're going to graph the function y is equal to 3 cotangent of 1/2 x. Y is equal to 3 cotangent 1/2 x for 3 periods. So A is equal to 3, in other words, it's positive. That's really the important part. B is equal to 1/2. And so therefore the period would be pi over 1/2, or in other words, 2 pi. There's no phase shift, there's no vertical shift, so we're just going to practice a straightforward cotangent one here. So the second thing we need to do is figure out what the asymptotes are. Remember, the first equation is 1/2 x is equal to 0, and the second equation would be 1/2 x is equal to pi. Because the asymptotes are bounding it on 0 and pi. So we have 0 and 2 pi.
So you'll always get 0 for the first asymptote.
Unless we phase shifted it, yeah.
Yeah.
I would say most of the time, unless I'm proved wrong. I don't like always. So those are our asymptotes. Now we're ready to sketch it. So I have 0, 2 pi. I'm going to cross at pi. So I've got asymptotes Now, remember when you're drawing asymptotes and if your asymptote falls on an axis, like in this case, it's falling on the y-axis, then you just need to identify it with dotted lines above and below. That indicates that it's got an asymptote right there. And then we have an asymptote at 2 pi. This is cotangent, so we are going to come from the left cross and go down to the right. I drew 2 periods, but you can figure out how to draw 3. All right, so sine, cosine, secant, and cosecant. They're all graphed the same way, right? What's the period for those 4? 2 pi over b, that's right. And we've practiced enough of those, I think, that you can graph those. Tangent and cotangent are the ones that have a period of pi over b. That's right. And so they have those special, and also they've got those considerations as far as those vertical asymptotes. Tangent is centered at the origin, bounded on the left and the right by negative pi over 2 and pi over 2. That's how I remember those equations for tangent. Cotangent gets shifted, and it has boundaries on its left and right at 0 pi. And that's how I remember those asymptotes. Okay? All right, so you need to practice these. Okay, I believe that the Desmos activity that I have listed is only covering sines and cosines, but it does cover all the aspects as far as amplitude, period, phase shift, and vertical shift. So you need to be very familiar with those because those concepts will still apply here, right? They put tangent and cotangent, all right? And we're going to talk about inverse functions tomorrow and do a little bit more practicing on our graphing. Okay? All right. If you have any questions, let me know. Otherwise, I'll see you back here later.